Good afternoon, everybody. It's Peter Coombs here at XP Solutions. So we're looking at the fourth part of our series on how to design sustainable drainage systems in the Middle East utilizing microdrainage. So looking at the agenda for today, what we plan to do now is take the model that we've put together last time and check its hydraulic performance. So what we're going to do is look at a range of storm events, and these will be not just a range of return periods, but a range of storm durations within return periods. That'll be more clear when I show you the software live with the live demo. We're then going to make sure that everything is working in accordance with your local standard. Let's make sure that there is no flooding for the 25-year, the 50-year, whatever the requirements are. We can design towards those requirements and then audit towards those requirements. But then what I want to do is go beyond that, because what we're experiencing, not just in the Middle East, but across Europe and the Middle East, is a range of flooding events that are unpredictable. They're very extreme, and they're becoming more frequent. So what we plan to do is to account for this shift in climate change, and we can add in additional rainfall intensities and go way beyond the design and deliberately, with the purpose of creating overland flood routing, to just test where that water is going to flow and make sure that we're controlling that water. So we're going from design of drainage systems now into surface water management territory, and we can assess those overland flood flow paths and make sure that we're controlling them in the highways, for example. And I'll just do a couple of slides and then we'll run live with the demo. So just to remind ourselves, I mean, we have some new attendees today. So what we've done, we've run through a series of, it's a systematic approach on sustainable drainage design. And that started off with planning out of where we can put these particular structures, whether they're basins or wetlands, those kind of structures, swales, etc. So there's a lot of planning thought required to make the space for the water, to make this a better environment, and to consider the overland flood routes even at the beginning of the design process. This is one of the fundamentals that we need to do. Then we've designed a flow conveyance system, and we've then created an integrated model by adding into that system flow controls to limit discharges off-site, and also we've added in a range of structures to complete an integrated model to then provide us with multiple benefits and to minimize the cost of construction, because should we be able to infiltrate into the ground, that can save quite a high volume of water storage under the ground, and it's that volume of water storage that costs an extra amount of money. So today what we've planned to do is to look at the model that we've created, audit the model in accordance with the standard, and then go beyond to look at risk management. With the risk management, the intention is to look at where this overland flood routing is going. So when we do get a very extreme event in some point in the future of some unpredictable time or scale, where is that water going to go? And we can see on the graphic here, the water is flowing across the surface terrain. It's coming up towards the housing, and the water depth is increasing, where the color of the water changes from blue to red and yellow. That's deeper water. The red and yellow zones are showing you the deeper water backing up against. And we can see where the water is flowing along the highways. Now, there are some draft standards in the Middle East that will be coming out probably by the end of the year. I'm not sure if you've all had access or have been consulted on these, but essentially what the standards are asking us to do is to look at this exceedance and control it within the highway, and control the maximum depth of flow in the highway, and also the amount of time that it is at that depth, whether it be 100 millimeters deep or 150 millimeters deep. But this is something that's going to come your way, so you need to be aware of this, and you need to be able to do this work. And as I say, I believe the standards will be coming out probably by the end of the year. unfortunately, we have an awful lot of experience going back decades on where we failed to do this in the developed world. And the graphic in the bottom right-hand corner is showing you an existing development, and what's happening here is the water, the runoff is creating flooding. The flooding where we see the orange, the green, and then the red is a higher depth or deeper section of water building up against, it could just be a fence or a wall, and then the wall is collapsing over a certain distance. So this is the experience that we have, and what we want to do with our designs is avoid that in the first place. However, when we have existing problems, and this is again happening increasingly frequently throughout Europe and the Middle East, we have to mitigate against these issues, and that costs a lot more money to mitigate than it would have done to have designed more appropriately in the first place. Okay, so what we're trying to do, we're trying to generate multiple benefits with our sustainable drainage systems. We need to ensure that they're affordable, so we put in a compliant design but at the minimum cost. Ensure that they're robust, we go beyond the design and ensure that we are controlling and fully aware of how we can manage that surface water, and ensure that we're putting systems in that are going to be maintainable. It's one of the big issues everywhere. A lack of maintenance is often the cause of such flooding, as we see on the right-hand side, actually. So there will be 2 steps to the live demonstration. So in true Blue Peter fashion, here's the one we've done earlier. So this is the network that we generated last time. We added in a range of different storage structures, and if I just click on the audio play, what I've done here, I've analyzed one particular event. It's a 50-year return period, 60-minute storm duration, and this is the consequence of that particular event. There is actually no flooding, and I can check this in a couple of ways, but I can show you the summary of the results. So if I just click on the sum, there's an icon under the window drop-down. So if I click on sum, we can see that if I just move the video controls to one side, that we have a summary of results for the measured rainfall for the 50-year return period, 1 hour storm duration. And if I was to scroll down on the right-hand side, these are all the different pipes and manholes, including the structures. So you'll notice, I know it's a lot of spreadsheet type numbers here, but interesting to highlight the extra columns that I've switched on here. There's a column that is showing you the flow out of the network through an infiltration structure into the ground. So this is the flow rate into the ground for this particular event, and also the volume. The volume that's actually been discharged into the ground throughout this event. So it's, in this case, 2.8 liters per second, and just under 20 cubic meters of volume has infiltrated out of the network into the ground, and that's obviously saved 20 cubic meters of storage under the ground. What are those structures? If I just click on the network drop-down, and we can see which structures are in the model. I just scroll down towards the pond brackets tank stroke storage structure icon. We can see that you have a range of structures, trench soakaways, infiltration basins, a complex structure at the downstream end, and if we look at that by clicking on the edit drop down, this complex structure, before we discharge off the site, is an infiltration trench seated beneath an infiltration basin. So back to the photograph that we saw in the first instance with the kind of brown infiltration basin area, that type of basin could have a trench with porous fill within it underneath, for example. We can build up more layers than this, but that's just to show you an example. Okay. So how did we analyze for this particular event, and how do we control the discharge? If I click on cancel and say no to that, I'll just show you the setup by clicking on the site drop down and the simulation criteria. So this is where I loaded in the rainfall profile by clicking on Edit and then loading in the either the RED or REDX file for the 50-year return period, 60-minute storm duration. And then I clicked OK, and then hit the green for Go button. Or we could click on the Analyze drop-down. There's a warning that there's a particularly steep pipe in the network, but that's just a limitation of the profile of the ground. So I click on Save, and that was the amount of time it took me to analyze this particular event. Now, on the right-hand side, we can see that there are a range of status. So for each location in the network, at every manhole location, every node location, we can see what the effect of this event and the runoff generated for this event has had on the pipe and its manhole upstream. Now, there are a series of flags on the top of the screen here on the left-hand side. So I could click off all of the pipes that are saying OK. So there are 4 types of status. OK means the flow is still within the pipe. So that's fine. Surcharged means the flow in the network is above the soffit of the pipe, but it's still within the manhole under the ground. So it's not flooding. If I click off all the surcharged, we're left with 2 other types of status, either flood risk, where the water is getting very close to the ground level, and flood, where the water is coming out of the network and across the surface. And we can see we've either got OK or surcharge for this particular event. In other words, the water is not getting any closer than, say, 300 millimeters of the ground level, and there is no flooding. So at first glance, you think, well, that's absolutely fine, job done, but that is only one event. That's only one one-hour event for the 50-year return period. What I'd like to show you now is how we can audit for all the different return periods and all the different storm durations in one run. And to do that, I'm going to use some rainfall files that are used over in the Middle East. And there are a series of wizards. I'm going to run 2. The first one being, if I click on the wizards drop-down, the rainfall wizard. I click on rainfall wizard. We can reset a CV to anything from 1 and below. I'll leave the default value there, but if I click on next, just go through a step-by-step process. How did I put these rainfall profiles into this step? I added them by clicking on the Add Rainfall Files. And we can add in either an REDX format or a .RED format, which is output from modeling software used in the Middle East. So your clients, if they're modeling with third-party software, you can export the rainfall files in a .RED format that we can then read in. And that's what I've done. Here are all the different events ranging from the 2-year return period, 1-hour storm duration, all the way up to the 50-year return period. If I click on the Shift key and left click, I could select every single one of those events. So it ranges all the way up to the 50-year return period, 12-hour storm duration. And then I said open. I just say cancel now. It literally just popped all of the files into that step. So we can see all of them have been brought across. I'll run this live with the climate change wizard in a second as well. And we click on the next button, and then we finish and analyze. And again, the warning about the very steep pipe will pop up, but that's okay. It'll still analyze that. And we will then run the analysis in something like a minute. Now, at the end of this process, what we'd like to do is identify what is the critical event. So I'll click on Save. What is the critical event for each location in the network? And of course, the bigger the network, the bigger the task this becomes. The storm selector has been populated and pops up for me. Now that shows me that at the minute we're looking at the results from the 2-year return period, 1 hour storm duration. But we could select by clicking on the drop down any one of those different events. I haven't counted these up, but there's, I don't know, 20 or 30 different events that we've just analyzed within less than 60 seconds. Okay, so we could choose any of these, maybe the 50-year 12-hour storm duration, and you can see how the status will change and the flows in the pipes will change, etc., etc. But what I'd like to do is show you how to sort out what the worst case is for each individual location in the network. And to do that, we just click on a little red warning triangle, top left-hand corner of the screen, which is now sorting out the critical storms for each location in the network. And if I scroll along to the left-hand side of the summary of the results, you can now see that there are a range of different return periods and storm durations. So the sensitivities of this network that we've designed has now been highlighted. And what we should do is make a note of each and every one of the critical ones here, and then run the analysis if we have flooding. So what I'll do, let me just turn off the OK, and I'll turn off the surcharge pipes. And that's telling me that even though we've checked every single return period and every single storm duration, there is no flooding on the network at all. So in other words, we are satisfying the requirements of the client in terms of no flooding for the 50-year return period, should that be your requirements. And the worst case scenario is we're discharging at a rate of 46.3 liters per second off of the site, and it's the 50-year 2-hour storm duration that's sensitive towards the downstream end of the site, where that complex structure is comprising of the basin with the trench underneath it. How did we limit the discharge off of the site? We put in a flow control, and I can show you the network drop down, and where we looked at the structures before, we can now look at the online controls. And you can see that there are actually not just one flow control, but there are 2 flow controls within this network, somewhere midway down, so utilizing the attenuation further upstream of the site. But then at the outfall location, we have a hydro brake, which is a vortex control, which is the most common flow control that I'm aware of being used everywhere in the Middle East. So you can see that it's been set to ensure that we're discharging off-site at a design flow, maximum design flow of 50 liters per second, and we have a maximum head acting upon it of 1.5. So there's the flow curve and the kick point. So it's satisfying the requirement of 50 liters per second maximum discharge, as well as ensuring that there is no flooding. So audited, and everyone should be happy. Not going to make any changes. What I'd like to do, though, is now go way beyond that design, and let's look at climate change. Let's look at the impact of what climate change would have upon this network. We know that it's fine and okay for the events that we've generated, but what happens if we go way beyond that at some point in the future? So if I click on the wizards drop down, I'm going to select now the rainfall climate change stroke sensitivity wizard. And again, I just go through a simple, straightforward, step-by-step process, and I'll add those rainfall files in as I showed you earlier on. So if I just click on the .red file format, these are all the rainfall profiles from the 2-year return period all the way up to the 50. I just say open to that. So they've all been incorporated. On the next step, we can now put in sensitivities. So this is now going to either take away or add an additional percentage upon the rainfall intensity of those rainfall hyetographs. So the study that came out from the MMUP in Qatar, for example, in Doha. They have looked at a range of climate change impacts. So what we could do, if I clear all, unfortunately they're not getting negative impacts, they're getting positive impacts. So we could add in, say, an extra 10% for climate change. We could add in an extra, let's say, 50% rainfall intensity for climate change, or maybe 100%, or maybe 200%, 1,000%. You see where I'm coming from? You can add in as many different additional rainfall intensities as you wish. Okay. If I click on Next, and then click on Finish, and stay OK to the warning because of that steep pipe, the program will now analyze each and every one of those rainfall events and add to each of those an additional 10%, additional 20%, 50%, 100%, 200%. So we're now going way beyond the design, and we're looking far into the future and analyzing what will happen if. And once again, when the analysis has taken place, and I wanted to run this live for you to show you how much time and effort this takes. This is not days of work. This is hours of work. Obviously, the larger the network, then the longer it will take to run the analysis. But typically we're taking minutes and sometimes hours to run the analysis on the industrial cities, for example. Okay, we're being asked, can we test for blockages, etc., etc.? Yeah, we can. What I'd do for blockages, to be honest with you, I would, rather than using the sensitivity analysis, I would run with the additional rainfall intensities, but then I'd introduce an online control, for example, that would be a weir up to the ground level that would then effectively block the flow going downstream. Or what we could do is we could add in sedimentation depths. And of course, there's a lot of sand and fines that get into our networks. So if you had half of the pipe or a proportion of the pipe silted up, we could replicate that within the network details as well. Okay, so the analysis has taken place. I again can click on the little warning triangle at the top of the on the top toolbar, which has now identified the critical storm for each and every location within the network. And you can see on the right-hand side that it may not please the auditor, but it pleases me to see some flooding and flood risk. So you have all four type of status now being shown on the right-hand side of the screen. We still have some pipes that are still flowing okay, as it happens, so no problem at all. There are some that are surcharged, others with flood risk, so the water is coming to within 300 millimeters of the ground level. And then we have flood. And if it did flood, it's telling us the volume of flooding. Okay. And if I slide to the left-hand side of the screen for you, and if I switch off the OK pipes because they're okay, if I even switch off the surcharged pipes because they're okay and still under the ground, we're now left with the more sensitive areas of flood risk and flooding. And towards the bottom you can see that we've got over 1,000 cubic meters of flooding coming out of manhole number 44, for example. Okay, so if I move over to the left-hand side, we can see that we're getting the worst case flood. If I turn off the flood risk and then move over to the left-hand side again, the worst case flood is probably the 1 hour storm duration for the 50-year return period with 200% additional rainfall intensity because of climate change. So yeah, still around some, even in there, some sensitivities are even a 25-year. So this is what really fascinates me. And at the click of a button, you can get a really good feeling as to how this whole system will perform under a variety of different events. So what I'm going to do now, I want to just focus upon one, but I would normally take a note of each and every one of these and run the following analysis for you. But let us just focus upon the 50-year return period 1 hour storm duration, and let's add in 200% for rainfall intensity. How do we identify where the water, where this flooded volume is going? I mean, 8 cubic meters doesn't sound too much, 3 cubic meters. 76, I can visualize this coming out of the manhole and spreading out very, very thinly. When I get to 1,000, I'm now starting to think, this is where we could end up with issues and the road being blocked, and for what period of time. So what I'm going to do now is show you how to set up the simulation criteria to replicate this, one of these worst case scenarios, 50-year, 1 hour storm duration with additional 200% for climate change on the intensity of the rainfall, and then show where the flooding is going across the site. As importantly, make sure that we protect the properties. This isn't now upsizing everything under the ground. This is now surface water management. So can we raise curbs? Can we reposition some buildings, etc., etc.? We're going to look at what we could potentially do, having identified the extent of the issue. So to run this one event, I'm going to click on the site drop-down, simulation criteria, and run this worst case. It's the 50-year, 1 hour storm duration that I happen to have had in the simulation criteria in the first place. So I don't have to sort of click on edit and then load in another profile. And then I'll add in the additional percentage of 200, which is replicating the climate change. Now if I say OK to this, in the background you'll notice that the screen will automatically rerun the summary of results, and the results will pop back with the flooding that is coming from this one event across the entire network. Okay, so we can now scroll down and see that we've actually got now 847 cubic meters of flooding coming out of the manhole at the bottom, and then around about 20, maybe up to 40, 45, further back up the network. We can take a look at this visually after analyzing, utilizing the flood flow module. So I'm going to click on Analyze and then choose Flood Flow Analysis. So tell me where the flooding is going across the site. The grid size we can select. We can't have a variable grid size. We can only have 1 by 1 or 2 by 2 or up to 50 by 50. So it depends on the size of the site. I'll choose a 2 meter by 2 meter grid square size. The surface roughness, what's the surface roughness? Is it urbanized? Is it rural? Have I zoned the CAD drawing? I haven't, so I'm just going to say this is an urbanized, like a tarmac surface. And what's the analysis type? Static, dynamic, or am I applying rainfall directly onto the grid? I'm going to choose static analysis. And what this means is that when flooding comes out of the network, it will not be allowed to re-enter the network. It's the worst case scenario. And if I say OK to that, whilst that's running, I can explain that if I had chosen dynamic analysis, then the flooding going across the surface would have been allowed to have re-entered the underground network. So it's the 1D, 2D linkage would have been red, and the flow would have been allowed to have re-entered at various manhole locations. And we assume that there are 4 gully entries at each manhole location. So the flow that would be allowed into a standard gully, a British standard gully, would be allowed to flow back into the underground network. So you have that 1D to 2D interface happening. With the apply rainfall directly onto the grid itself, it has the same effect in it. The runoff that's generated on the surface will then be enabled to flow into the underground network through those 4 gully entrants. And then if the flooding came out across the surface, it would be allowed to re-enter as well. So I've chosen the static because, as I say, this is the worst case scenario. The flooding is coming out at various manhole locations. How's the runoff entering into the network? It's being generated on a sort of catchment subcatchment basis. So we've identified what areas of what impermeable areas are entering into each of the manhole locations, and that runoff has then been analyzed and applied at each of those manholes. When the flooding comes out, it will run across the surface, not be allowed back into the underground network, and it will continually run until it falls off the end of the model. And this is the analysis that's taking place right now. So as you can see, on a 2 meter by 2 meter grid square basis, probably going to take about 3 or 4 minutes to run, something like that. So whilst that's running, I'll have a very quick look at the questions coming in. Is there a way of specifying walls in the CAD drawing, or does it have to be incorporated into the tin? That's a nice question. No, we actually have to apply the walls off of the tin there. What I'm going to do, this is coming to the end of the series on design, but it's leading nicely into modeling of existing systems and analyzing flooding. Now, to do that kind of work with existing networks, there's a lot of GIS type data, so and CAD data as well. Now we use the XP Swim with 2Flow to run the analysis on a sort of city by city scale. So that's the next series that I'm planning to run, and within that we can pick up things like solid objects, etc., fences or walls, if they're in the GIS layer, for example. So the first part of that series will be importing external data, importing third-party data. So maybe we can show you something like that with XP Swim. But with the flood flow, no, we can see visually where the fences are, but we'd have to build a wall up off of the tin in MicroDrainage. We'll just wait for this analysis to run, and I'll answer another couple of the questions that have come in whilst we've been presenting. One of them is asking about the flood risk. How can we set the flood risk levels in inputting Excel data? We're very sensitive to inputting Excel data on account that we don't want people using Excel to design their systems and then importing them into MicroDrainage and saying, hey, look at what MicroDrainage has designed. So we can import certain Excel data, like rainfall data, manhole coordinates and things like that, that they're not going to be particularly sensitive, but yeah, we limit on what we can import through Excel, less so with XP Swim. So again, I'd like to show you that at the next webinar with XP Swim. It's a modeling software, so it is what it is. So we're less sensitive to it being outputting design criteria that we've designed with industry standard software. Okay, so we now have our results. I'll show you where we can reset the flood risk for Paul's query here. So on the file drop-down, if I go down to the preferences, okay, you can see here in simulation where the flood risk is set. So we were looking at the summary of simulation, or summary of results rather, in simulation. So that's where we can reset it. It defaults to 300 millimeters, so you might want to set that down at 500 millimeters, or maybe a meter below the ground level. And one of the points I raised earlier was when I click on OK, you'll see the results rerunning in the background. This is the analysis, the maintain results. So every time you make a change, the program will automatically rerun the analysis. It saves me that awful headache of going up here and hitting the green for go button. So that could be irritating if you're making a lot of changes, and you may want to switch that off. So if I click on the maintain results, you could say no, just make it user specified. So analyze and reanalyze when I tell you I want to analyze, not every time I make a change. Okay. So we've got our results back, and if I just zoom in a little bit, this is now showing us the results from the flooding analysis. So as I showed you earlier on with the video controls, we can now run this maybe double time live, and you can now see where flooding is coming out of the network, down along the highway, through the properties, up against the properties, and then flowing off the edge of the digital train model. And the colors important in terms of depth ranges. So just slide this on to the end. There we are. So there's our maximum depth of water. The color of the grid square, remember it's a 2 meter by 2 meter grid square, the color of the grid square is telling me the maximum depth of water that has flowed across that grid square through the duration of this particular event, which is the 50-year, 1 hour storm duration with 200% additional rainfall intensity added to the HIUTI graph. And if I right click on the mouse and look at the display settings, move that form over to the left-hand side of the screen for you a little bit. So we can look at the flood flow colors and the depth of water. It may look shocking and awash, but actually the minimum depth of water being shown is 15 millimeters. So anything shallower than 15 millimeters is not being shown. Now the draft standards that are coming out, one of them that I've had a look at this week for the Middle East, is that what they would like is, well, two different depths really. One scenario is with some local roads, and they want the local roads to have no more than 100 millimeters of water depth, and that water should be less than 100 millimeters within an hour, if that makes sense. So in other words, don't show me anything less than 100 millimeters is what I'm adding in there, and then go to 150 millimeters. So between 100 millimeters depth and 150 millimeters depth, show it to me in blue is effectively what I'm asking the program to do here. And then from 150 to 300 millimeters, show it to me in red. But don't show me anything shallower than 100 mil, because the criteria from the Public Works Department is to make sure that we don't have anything for more than an hour 100 millimeters deep in the highway. If I apply that, this is now focusing on those areas that could be non-compliant. So immediately it cleans up the screen and it takes away an awful lot of the issue. So we're going to find that in this area here, between 100 to 150 millimeters, if this is the local road that they say should not be underwater for an hour with 100 mil or more, we've got to do something about this. We'd have to sort that out. We'd also have to sort out the fact that we're flooding a property here as well, because if I refresh the display settings here, the red is telling me that the water is between 150 and 300 millimeters deep. Well, that's over the threshold of a property, so we've got potential flooding issues here and there, and at the bottom here as well. So we're now focusing on the areas at most risk. And once again, we could save out the image of this to AutoCAD, so we can save this out as a DXF or a DWG. Okay, and if I typed in Middle East webinars, webinar 4, and we said flood and greater than 100, and save that. Oh, no, of course I can't do that. Doesn't like me using the greater than, of course. Flood 100 plus. I won't be able to put a plus in there either as well. It then pops up with the export options. What do I want to export? All the visible layers as 2D, or do we want to save out the 3D as well? So we could save this out, and you can import this into AutoCAD or Civil 3D, and you will see the extents of the flooding on your CAD drawings within CAD. And we would bring in the underground 1D network, all the pipes, all the manholes as 3D entities. Okay, So this is complying with your BIM requirements. So every time I visit the Middle East, I'm hearing about how you need to generate BIM, how you need to now go beyond and look at climate change and exceedance, and carry out all this kind of work. So it's already there. So we just need to help you to get up to speed. Okay. Good. What we can do now, I just want to make it a little bit more exciting. So let me change the display settings one more time. It's not the most difficult of jobs. So let's go for half the depth of a threshold, 75 millimeters. Say apply. And then at least we can see a little bit more flooding going down the highways, etc. And we can take a look at this in the 3D world view by clicking on the 3D button on the top toolbar. Now what I should do is just come in here and add in my top toolbar. I'm just looking at the ground options here. I've taken the ground off when I showed you the flow going through the network with no flooding earlier on. So now I could either put on the wireframe ground or transparent ground. Kind of works for me because we can see through it, but you will have the CAD drawing applied onto the surface. Just want to make sure the surface is showing the triangulated ground model. And then if I right click, we've now got the option to sort of pan and move things around here. So if I just spin this around a little bit, we've got a new compass over on the left hand side. This is one of the features that many people were asking us for. They had issues with the old compass setting, so now we've got a new compass and an option from the mouse to spin things around. And let's have a look at where this flooding's going now. Bearing in mind that the blue is from 75 millimeters up to 150 millimeters deep. And I could maybe actually slow that down, grab the slider, and this is interesting because bearing in mind the event is an hour long, you can see the timing going through here minute by minute. So there we are. We're at the hour point, an hour and 3 minutes. Okay, this is where the water is going to be an hour and 3 minutes into the event. So we can just step back a couple of places to, there we go. There we are, 59 minutes. This is where we shouldn't have any water 100 millimeters deep and above lying in the highway. Okay, so that is giving you a stark output. I could go back to the plan view, export that into AutoCAD, but obviously I would do the mitigation. I'd make sure that it wasn't sitting in the highway, so it would get approval by the Public Works Department before I showed them that. But there we are. That, I hope, explains how you can work with the software and create very, very good outputs. This, by the way, I could record the animation and you could put that into a PowerPoint slideshow, which is how I showed you the plan views, etc., in the earlier PowerPoint slideshow. So it's as easy as that. It saves out in an ABI format that you can just straight input into PowerPoint. Just looking at the question on the screen here, flooding in the model that I've just gone from is from lesser diameters, question mark, and is it resulting in backflow from the manholes? And what exactly have we assumed? Yeah, what we've done, we've designed that completely integrated system, and that does comprise of pipes and structures and flow controls. And the flooding has occurred because we've applied really intense rainfall, taking into account climate change. So there's a lot more runoff now being generated on that design network than it was designed to take. So we have deliberately created flooding, and it's identified the pinch points. It's telling us where the problems are occurring and where they are likely to occur in the future. And there's another question about the results spreadsheet, and there's a cyan blue row. That cyan blue is telling me that the capacity of the pipe has been exceeded by greater than 200% of its capacity. So that's a real pinch point in the network. So when you have networks designed in microdrainage that are sort of thousands of pipes, you can see at a glance where those pinch points are, and that's probably the likelihood of where flooding will first occur. Not guaranteed, but it's likely that that's where flooding is going to occur, and it's a good indicator as to where we ought to be considering applying the storage structures. Okay, so when we're looking at attenuating and holding back flows and providing source control right back at source, it's identifying areas that would make sense to put the structures in place. So thank you very much for the questions. Hoping that what this series has done for you is enabled you to see how we can better plan and design sustainable drainage systems for all these new developments that are happening all over the Middle East. Okay, for that we use the MicroDrainage program. Where we've ended up is getting to the stage where we have a range of flooding for when that design fails. Now, unfortunately, as I mentioned before, we have an awful lot of experience analyzing existing networks and now putting in flood alleviation measures shown in the bottom right-hand corner, and for that we use the XP Swim with 2Flow software package. So what I'm planning to do now is to move into how do we fix existing problems. Basically, I want to look at how we can model existing drainage systems and then model the flooding. So to start with, in the first event, we're going to look at importing data. So how do we import GIS, CAD, Excel, all that third-party information to build up a picture of what's there right now. In the second part, I want to show how to model a wadi. So let's get the flow running through a wadi or a creek or a river and bring in the drainage networks, the existing drainage networks. And those drainage networks could be surface water, they could be sanitary, they could be combined. And this is what I'm showing on the right-hand side, is a video of flooding. So I want to link the flow conveyance, the existing flow conveyance network, the drainage systems, and that could be the wadi with the pipe network as 1D, and get the flow running through those, and then create flooding for those extreme events, and show the interaction between the 1D and the 2D, but with modeling software rather than design software. And at the end of that, we will have a range of flood risk maps that we can identify and output, and identify evacuation routes, because looking at the city on the right-hand side here in flood, how much time do you have? You know, where are the sensitive buildings? You know, is this a school building? Is this a hospital? How much time do we have for the emergency services to come in here and evacuate the vulnerable? And this is what we're having to do all across Europe under the flood risk regulations. And it's happening increasingly in the Middle East as well. So that's the plan for the next series, to which you're all cordially invited and would be more than welcome to attend. Thank you one and all, and look forward to keeping in touch and speaking again. Bye for now.